In this problem, we have a vertical Atwood machine where the mass of the pulley is not negligible. So we're going to use conservation of energy to approach this. And as the system evolves, the potential energy of the 2 kilogram mass decreases. The potential energy of the 1 kilogram mass increases. But that's a net win. My net decrease in gravitational potential energy is greater than the increase. And that's kind of the source of energy for the motion of all of these different pieces. In my final state, I have both of these masses moving and I have the pulley rotating. So that drop, the net drop in gravitational potential energy has been pumped into these 3 different instances of kinetic energy. So let's be clear about what our origin is for the y coordinate. I'm going to put it at the lowest point in the problem. And that means the initial y for my 2 kilogram mass was 30 centimeters or 0.3 meters. My 1 kilogram mass starts at 0 and ends up at 30. So let's write down our energy conservation equation. And in my initial state, all I've got is one non-zero term. It's just the potential energy of the 2 kilogram mass. So that's going to be an mgy for that. So I'm just going to go ahead and start putting numbers in right away this time. 2 times 9.8 times 0.3. In my final state, my 1 kilogram mass has some gravitational potential energy. That's 1 times 9.8 times 0.3. And I have 3 things moving. I have a 1 kilogram mass moving with an unknown speed squared. I have a 2 kilogram mass moving with exactly the same speed because this string is not stretchy. And then I have a 1/2 I omega squared for the rotating disk. If I subtract this 1 times 9.8 times 0.3 from both sides, I end up with a net of 1 times 9.8 times 0.3, which ends up computing to 2.94 joules. Over on the right-hand side, I have 1/2 times 1 times v squared plus 1/2 times 2 times v squared, which is 1/2 times 3 times v squared, so 3/2 v squared. And then I want to put in the formula for the moment of inertia of this heavy disk. And I'm going to leave that symbolic for a second because I have something to cancel out. Now I need to figure out how to relate omega to v. And I think it's important to talk through this. The 2 kilogram mass is moving with the speed of v, which means that the string itself is moving with the speed of v. But that means the string is moving with the speed of v right there where it's touching the disk. And I know the string is not slipping, so it must be moving at exactly the same speed as the edge of the disk right there. So with the edge of the disk moving with the speed of v, and given a radius of the disk, r, I have a simple formula that relates these things. V is equal to r omega, and that means omega is v over r. So I'm going to make that substitution into my energy equation now. I'll go ahead and multiply the 1/2. And I left that symbolic because omega is going to be v over r. And when I square that, the r's are going to cancel. So it doesn't even matter what the radius of this disk is. We'll keep cleaning things up. 2.94 is 3/2. And I'm going to factor out a v squared now. Plus 1/4 times the mass 1.5 times v squared. And when I crunch those numbers, I get 1.875 v squared is equal to 2.94. And solving for v, I get 1.25 meters per second. In part B, I want the rotational kinetic energy of the pulley. So you could say, well, that's going to be 1/2 I omega squared, so I have to compute omega. Or I could just go back and look at what I was doing back here to the rotational kinetic energy term. And it turned out, well, if I replace omega with v over r, I with 1/2 mr squared, the r's cancel out. And I end up with a 1/4 times the mass of this thing, which was 1.5 kilograms, times the speed at its edge, which is the same as the speed of those masses that are moving translationally. So that's 1.25 all squared. And when I crunch these numbers, I get 0.586 joules of energy in the rotating disk.